welcome. I'm glad you're all here for this comps talk. If you are a senior and you are here, please keep your video on to support your fellow compser. It's nicer to give a talk when you see people staring back at you than when you see a bunch of empty boxes. Also, make sure your name is your actual name so that when Trini takes attendance, you can get credit for coming here. Directly after the talk, there'll be a question and answer section. So if you have questions, you can either write them in the chat during the talk, or you can save them up and write the question in the chat after. You don't have to write the whole question. You can just put a question mark or say question, however you want. And then I will sort of lead a question and answer session. So I'll call on you. At that point, please unmute yourself and ask your question. And then after the question and answer session, Valerie and I will stick around and ask Fred a few questions. So we'll ask you all to excuse yourselves from the Zoom at that point. Up until the questions, I'm going to ask that you stay muted so that it's a nice clean talk and we can hear everything that Fred says. And then I guess all I have left to say is that I would like Lucy to introduce today's speaker.
Hi, everybody. Welcome to Fred's Comps. I got to know Fred through Cars Club and our mutual enthusiasm about engineering. And I say this with complete honesty that I'm super excited for his topic. It's very uplifting. So without further ado, Fred, if you could take it away about the Raptor engine. I know it's going to be a blast.
Thanks, Lucy. And thank you everyone for coming to this talk. I'm going to be giving you an overview of the Raptor engine, which is a rocket engine that's being used on the SpaceX Starship launch vehicle. So a little overview of this talk. We're going to start out with some motivation, or why you should care about spaceflight technology at this specific point in time, and why it really matters. Then we're going to jump into the fundamentals of rocket propulsion and thermodynamic engines. Then we're going to take a step back from the engine. We're going to talk about the dynamics of a rocket in flight, and we're going to use that to motivate a key engine parameter that defines efficiency. Then we're going to jump into the fluid mechanics going on inside the engine, figure out what variables are affecting the parameter we defined from the dynamic section. And then we're going to go into engineering to figure out how we make all this stuff work. So motivation. So in 1969, we landed humans on the surface of the moon. And from that point onwards, our capabilities in space have been decreasing. We've been regressing. In 75, we canceled the Apollo program. We could no longer go to the moon. In 2011, we canceled the shuttle program. We could no longer send humans into orbit. And if this trend actually continues in the future, in 2025, the ISS is going to be decommissioned. So public exploration of space has been on the decline. And while that's not very motivating, the fact that private industry has gone ahead and taken up the mantle is very inspiring. So SpaceX just last year launched 2 humans into orbit. And this was the first time a private company ever done this. And so SpaceX is trying to push that needle back to our sort of 1960s space exploration capabilities. They've only gotten to 2011 so far, but they're working on pushing us back to our old capabilities. Now, what's especially interesting is that their launch vehicle to do this, which is seen here in its first flight test, it's called Starship. Not only is this going to return us to our spaceflight exploration capabilities of the 1960s, but it's going to do it at a order of magnitude lower cost. So their entire vehicle is going to be reusable, both the lower and upper stages. And so that's going to bring down the cost immensely. So it's going to be around $10 to $20 to put 1 kilogram of mass on the surface of the moon, which is unprecedented. And it's going to usher in an insane amount of economic activity and scientific exploration and development. And I really think the next 50 years are going to be defined by space exploration and then this launch vehicle in particular. So what are we talking about? We're going to talk about the engine, the sort of the backbone of this vehicle that's allowing it to be so reusable and so efficient. So not only is this engine seen here in one of its static firearms, not only is it enabling this awesome vehicle, it is cool in and of itself. So it's the culmination of 60 years of rocket engine development and a lot of testing too, and a lot of blowing things up. That sort of started in the Cold War when rocket development split into two isolated camps, the Soviets and the United States. And those two camps developed very separate methods. And this engine is really the first time that the best of both worlds has been combined and brought into one sort of Goldilocks engine that has been called the king of all rocket engines. So it's a very exciting engine in its own right. Okay, so I hope that inspires you guys to pay attention. And so now let's just jump into some of the basics of rocket propulsion and engines. So most transportation systems are that we have on Earth are pushing off of other things, right? So a boat is going to be pushing or reacting off of the water. A plane is going to be pushing or reacting off of the air around it, and a car obviously reacting off the ground. In outer space, there's nothing to push against. There are some theories that at some point we may be able to utilize the quantum fluctuations in the vacuum and maybe transfer momentum to those instantaneously appearing particles. But all the methods that try to do that have failed. And so right now, the only way to move forward in space is to throw something behind you, is to push off of something that you already have, some mass that you already have on your vehicle. And the Newton's third law, reaction force from throwing that thing away from you is going to be the force that actually pushes you forward. So that's how a rocket works. It works by chucking stuff really, really quickly out the back. So how do we get that stuff that we're throwing behind us up to speed? And a common misconception is that it's like the explosion of the fuel and oxidizer. Remember, we need an oxidizer because we're in outer space, there's no oxygen. So in order to get a reaction, we need both. So the explosion is not really what's causing that gas to speed up. If you did, say, ignite all your fuel and oxidizer right off the bat, you would force your rocket forward, but the exhaust gases would expand at subsonic speeds, or actually it would be exactly sonic speed in a vacuum, but it would not go very far. You know, you could look up a video of a rocket blowing up on the pad. The highest thing doesn't go that high. And so what's really giving us this speed boost is this the geometry of this nozzle here. So what I want you to think about, what I want you to picture in your head is I want you to think about this combustion chamber as a heat injection point to a fluid that then gets compressed and expanded through this converging and diverging section. And it's that compression expansion that actually translates the initial heat from the combustion chamber into kinetic energy out the end of the nozzle. And so this nozzle shape is fundamental. Don't worry about these variables. We're going to actually return to this picture when we need them. So an important thing to note is that we're focusing on combustion. That's not necessarily the only way to inject heat into our system, right? So here's some examples. We could have an arc jet thruster that uses an electrical arc with a high voltage to heat up some working fluid, which then gets pushed through this converging diverging section. Alternatively, we could use a nuclear reactor to inject heat. And one interesting thing about this picture is you'll notice that we're using a hydrogen fuel tank here. And you might think, why are we using hydrogen if we're not actually going to be burning the hydrogen? Remember, the fuel is like uranium or whatever is the nuclear reactor is using. So keep that question in your mind. We're going to return to that later. Okay, so let's take a step back from the engine for a moment and let's talk about a rocket in flight and the dynamics that are involved. So really, as I was sort of alluding to earlier, this whole process is working through conservation of momentum, right? As you chuck something out the back, you're giving it momentum, but you're also giving yourself momentum in the opposite direction. And so let's use that to derive the rocket equation. So in this figure, I want you to imagine looking at a rocket that's stationary and then having it ignite its engines, and it zooms off in one direction and the exhaust mass zooms off in the other direction. And the total momentum of those two things is constant. We denote that with P sub T here. And then the momentum of the rocket and the gas are going to change over time. So it's important, this U variable here is exhaust velocity, and we measure that relative to the actual rocket. So not from our rest frame where we're standing and observing the situation. This is exhaust velocity relative to the rocket itself. This V is rest frame velocity of our rocket, and then this is mass and the change in mass over time. And note, it's important that this is a function of time because while a car burns its fuel to go forward, the change in fuel is so small we can just assume it's like constant mass. A rocket is burning over 95% of its mass as it goes from fully fueled to unfueled. So we have to account for changing mass in the dynamics. Okay, so I just applied a derivative to the equation above, and we know that the total momentum is going to be constant, and so this becomes 0. And we can then just move this derivative operator into these terms. This term actually needs some explaining. So V minus U is going to be the velocity of the gas in our rest frame. And that makes sense because remember, the U is relative to the rocket. So if we subtract off the absolute velocity of the rocket from it and subtract off the relative velocity of the gas, we get the absolute velocity of the gas. And so this term is going to be total momentum of the gas once you multiply by the mass flow rate and then integrate over time. So we can use the product rule here and the fundamental theorem of calculus on this integral, and we cancel these terms and we get this, which is the differential form of the rocket equation in deep space. And it's only in deep space because notice there's no other sources of momentum on the system, right? There's no external force that could cause an impulse, a net impulse on the system, right? So there's no gravity, there's no drag. We're just in deep space away from any gravitational bodies. Yeah, so this equation might look familiar. If you think about the 0 as being like no net forces, no external forces, mv dot is sort of like ma, or it is ma. And this term then must be the force of thrust on our rocket, and it is. And so one just like interesting thing that we can get from this is that if you want to build a rocket with more thrust and you sort of maxed out on how fast your exhaust gases are going, then you have to make the thing bigger, which adds mass, which can be bad. So let's integrate this equation, and we do so, and we can get the change in velocity is proportional to the exhaust velocity, and then there's this corrective factor which depends on the mass ratio. So what is this telling us? It's basically saying that our delta V, which is like what's the capability of a rocket, how much energy can we inject into our vehicle, is going to be basically solely dependent on the exhaust velocity of the engine of the stuff we throw behind us to create thrust. And so this U, exhaust velocity, is going to be the #1 parameter to judge rocket engines, because if a rocket engine can accelerate fluid better than another one, it's gonna have a higher exhaust velocity, and therefore it's going to make the entire vehicle more efficient. So exhaust velocity is going to be the parameter that we are going to be tracking through this whole talk. Okay, so we've motivated exhaust velocity as a parameter using the dynamics of spaceflight. Let's now go back to the engine and let's examine the fluid flow through that converging and diverging section, and let's see if we can get an expression for exhaust velocity so we know what actually affects it. So to start off, we're back at this picture. This time I want you to pay attention to the variables. Note that all these variables are going to be scalar functions of space and time. We can define the state at any point with a collection of these variables. So these are sort of like our state variables. We can't use traditional thermodynamic state variables like volume because we're not talking about any specific grouping of mass. We're just talking about a field, right, over space. And so if we do have a volume reference, it's going to be specific volume, which is volume divided by mass. And so we're going to talk about stuff like specific internal energy, right? Internal energy divided by mass, and specific enthalpy, which I'll get to. I'll define that. So yeah, these are sort of scalar fields. Another key thing is that we're going to make a quasi 1D assumption, which means that every cross section of this nozzle, we're going to assume that all these state variables are constant along the entire cross section. And that makes our variables effectively one-dimensional and just functions of x, which is going to be this direction. And that's brings in some error into our results, but we can deal with it. It's not that bad. One other thing, sorry, there's a lot on this slide, is that there's going to be 3 key sections here labeled with 1, T, and 2. And you can see the subscripts on our state variables are going to take up these labels to denote which section we're talking about. In general, a section could be any cross section, but these ones are important, so they're labeled. This is the state variables right before they enter the converging and diverging sections. So sort of like our initial conditions. Then this is the throat cross section, which we're not going to talk about that much. And then the exit plane is going to be our variables. Is going to be the section where our variables are in the state right as they exit. So that's going to give us stuff like exit velocity. And just one more note, we're not going to be using V here, we're using U. I'm sorry about that incongruency. Okay. So one thing we just need to assume, because it would take too long to prove, is the isentropic relation. And this is a relation between our state variables. We've got pressure, density, temperature at different sections, right? So this is temperature at section 2, section 1. This gamma here is a gas-specific constant that I'm going to talk a little bit about later. But although we're not going to derive this, I want you guys to just remember the assumptions we're using, the assumptions that we're assuming in order to use this, which is that the fluid passing through the nozzle is a perfect gas. And also there's no heat transfer from the fluid to the nozzle and then out into the environment. It's a completely adiabatic, is what that's called, system. And again, this assumption is not true, but again, the errors that it introduces are manageable. So this is the isentropic relation. Next thing we're going to use is going to be the continuity equation. So this is basically a statement of conservation of mass for a fluid. And we can show this informally if we just think about these integrals. So I want you to imagine we're back in 3D, by the way, to derive this, stepping away from our quasi 1D assumption. Imagine just a control volume with something flowing through it, right? And then a surface enclosing that. If we integrate over the entire volume, integrate the density over the entire volume, we're going to get the total mass. And then the time derivative of that is the change of the total mass inside the volume. Then here we have the flux, the mass flux through the surface. And so it makes sense that these sum together should be 0, right? Otherwise, you'd have mass appearing out of nowhere. And this is, just briefly, this is flux because this velocity dot surface element is, you can think of this as like the volume per second. If you imagine like the surface element being swept out for 1 second, and the amount it gets swept out is going to be proportional to the magnitude of the velocity. And then that volume gets multiplied by density here to give you mass flow rate. So sorry if that's rough, but that's all we have time to go over. And then if you ask Jay to party, I'm sure he will be happy to show you how to convert this into differential form by converting this integral converting this integral into a volume integral and then setting the integrand to 0. So that's the result we get here. Okay. One more variable that's quite important is enthalpy. Now, we're going to be using specific enthalpy for the reasons I mentioned before. And it's going to be defined as specific internal energy, E, times pressure times specific volume. And this is useful because it really isolates the effects of a heat injection on our system. Because the work, any work that's done gets canceled out by this PV term in the change in enthalpy expression. And so I'm not going to go through that, but just know that it's a useful variable to track heat injection. And so I've been saying informally we're converting heat into kinetic energy. That's actually incorrect. But heat is only a flow. What we're really doing is we're converting enthalpy into kinetic energy, from the chamber to the end of the nozzle. And it's enthalpy because we're getting energy, not enthalpy, from the chemical reaction, but the energy that goes into expanding the reactants to fit the volume that it's in, that energy is not usable to convert to kinetic energy because it already got used to expand the gas. So that's why we think of it as enthalpy conversion. Okay, so we've got enthalpy. Let's jump into a derivation of a simplified version of this energy equation, which is going to express the idea of conservation of energy in a fluid. And so this is very similar to the continuity equation, which was the mass conservation equation. We've just added in this total specific energy term here, which should make sense to you because we've got internal specific energy multiplied by specific kinetic energy. And then, as we saw before, PdV just gives us the mass at the differential element, and then we get the energy. So this is the change in total internal energy. Total energy, not just internal, total energy of the fluid in the volume. And this here is going to be energy flux for the same reasons. Now we set this equal to the work on the control volume done by pressure. And so that's what this is here. So again, we can, I'm skipping over how you convert to differential form, but this is what you get, this equation here in the differential form. And then this part here is just an algebra trick. I'm splitting up this dot product into two dot products, and this is sort of a vector version of the product rule. It's just a math trick. And I'm doing this because we're about to jump into some algebra. Okay, so here, this is just a standalone equation, does not follow from the last thing. But I just need to show this in order to plug it into the last thing. So if you combine if you go out and you do the quotient rule with this derivative and with this and with these derivatives here, and then you combine the results from the continuity equation, you get out this as your result. And I'm not going to show it, but everything that you need to go and do it by hand is on these slides. So you could do it on your own. And so now we have the result of this sort of arbitrary thing, but you're going to see why it's useful. We're going to plug in this P over rho term to our specific energy term here that we had in the differential form of the energy equation, right? So we're just going to add in this. And because these are all linear operators, the derivatives here, we can just add the result of this onto the other side of the equation, right? So we have a new equation, and this happens to nicely cancel with everything and give us just dp dt. Now, one thing to notice is that specific volume was normal volume over mass, right? Well, that happens to be 1 over density, right? So this is actually pressure times specific volume, which is the definition of enthalpy. And so we can convert these E plus P over rho terms into H. One last assumption we're going to make is that the flow is steady, which means that the flow variables only change over space. They don't change over time. And when this clicked for me, when I thought about looking at like a flow of water and looking at a single point and realizing that the flow variables don't change at that single point, even though if you move around in space, you're going to get different variables. At any single point, it's constant. And so these time derivatives just go to 0, right here and right here. So after that, all that, we finally get a result, which is that h plus the velocity squared over 2 is going to be constant over space. And so this is useful. We now have a quantity that from the beginning of our rocket converging diverging nozzle to the exhaust plane is going to be constant for that entire time, right? So we have a sort of simplified conservation of energy equation that's going to be really useful. And if we just plug in our quasi 1D assumption that we stepped away from earlier, we can just use U here, which is our one-dimensional velocity, and we call this term total enthalpy or static enthalpy, and it's constant over space. Okay, so we've got static enthalpy, we've got our isentropic relation. We need one more thing to fully derive exhaust velocity, and that is this relation here. So specific heat is just going to be the amount of heat that you need to raise the degree of an object for 1 degree. This is not specific heat. Sorry, this is heat capacity. Sorry, I misspoke. But yeah, so we have heat capacity is the amount of heat that you need to inject to raise the temperature 1 degree. We can substitute in the change in internal energy minus work for heat. And then we do some algebra and we get the differential form. And now we can divide by mass and get specific heat. And you'll notice that, total internal energy divided by mass is total specific internal energy. Volume divided by mass is specific volume. And heat capacity divided by mass is specific heat capacity. So that's where this equation comes from. Now we're going to make another assumption on top of our assumptions that there's no heat flow out of the fluid, there's no time derivative at any point, and the quasi 1D assumption. We're adding another assumption that the heat capacity is constant, and that's called a calorically perfect gas. And by assuming that, we get this nice relation that enthalpy is going to be proportional to temperature at any point. So finally, using that proportionality and using our isentropic relation and our static enthalpy equation, we can get these results. So we just we do some algebra here. We use our enthalpy temperature proportionality to set it equal to this, and then we solve for exit velocity, and we end up getting this. Now we can convert this term to this term using the isentropic relation, and we can convert this to CP, or that we can convert CP into these other gas-specific constants. And I'm not going to show that, but I hope you believe that just since these are just things that are specific to the gas, they should be interchangeable in a way. So K is Boltzmann's constant, M is the average molecular mass, and gamma is the ratio of the specific heats at constant pressure and constant volume. And so this is, we've arrived, right? We've got an expression for how fast our gas is moving as it exits our rocket. One more thing we're going to note is that U1, which is the velocity right at section 1, or at the end of the chamber, is going to be approximately 0 because the gas is moving very slow in the combustion chamber. We just think of the combustion chamber as adding heat, not velocity. So this pretty much goes to 0. So let's just look at this equation without the fluff around it for a second. There's really two things that stand out from this equation if you look at it for a while. The first one is that there's two ways to affect exhaust velocity. The first one that stands out is the chamber conditions, right? So the T1 and P1, if we raise those as much as possible, we're going to be raising U2 here, and that sort of makes sense, right? Because the more intense the chamber conditions, it's like we're pushing that gas through the nozzle with more and more intensity in a very informal sense. But I hope that makes sense intuitively. And then the other thing that stands out is the properties of our gas, right? So the average molecular mass plays a big role, and also this gamma here also plays a big role, and also in this exponent. So what we get is that if we decrease average molecular mass and we decrease heat capacity, specific heat capacity at constant pressure, this term and this term are going to move favorably for exhaust velocity. And it's interesting that the Soviet and United States programs, they when they were put into isolation in the Cold War, they looked at this equation and they came to different conclusions. The Americans decided, okay, easiest way, to improve efficiency is going to be with our chemical properties. We've got limitations with our mechanical engineering and our materials properties. Let's just focus on the fuels. The Russians said to themselves, chemistry isn't really our thing, but we're confident we can build combustion chambers that can handle more intense conditions, and so they focus on that sort of engineering. And then the Raptor is going to combine both approaches. So I hope you have a sense of what's really driving exhaust velocity with this. Oh, and one more thing about sort of the intuitive nature of the chemical properties. It makes sense that like a lower inertia particle would be more efficient, right? Because the whole point is we're trying to get these things up to speed. And so the lower inertia, like the better, right? And then the heat capacity also makes sense because we want these things to get up to temperature with as little heat input as possible. So that's some intuition on the chemical properties side. Yeah, so this is very important. This equation here is sort of the crux of the talk, I'd say. Okay, so let's just look at a little interesting interpretation of this equation. So you'll notice I've been talking about converting enthalpy to kinetic energy. But what if we just naively set final kinetic energy equal to initial enthalpy times some efficiency term? And we could naively say, oh, this is a thermodynamic engine. What if we just use thermodynamic efficiency or Carnot efficiency? And we plug in values and we get the exact same thing. So this is motivation for that idea that we're really, we're from that beginning plane of the converging section to that exit plane, we're really undergoing an energy transformation process using a thermodynamic engine. Yeah, so let's move on. So we've got our main methods of optimizing for exhaust velocity. Let's see how people have actually gone out and done this in practice. So first of all, fuel chemistry. We talked about why low average molecular mass and low specific heat are good, but we haven't talked about which gases have those properties, right? So I think, I mean, I'm not a chemist, but I think from these pictures, it's pretty clear which ones are going to be better, right? So you've got hydrogen, the entire thing can burn with oxygen, and there's like no waste, right? But if you burn like a longer carbon chain, all these hydrogens are going to burn off with the oxygen, and you're going to be left with this long, inertial chain of carbons, which is not only massive, but it's also going to be sooty, and it's going to gunk up your engine plumbing. So these are sort of the more complex in the molecule, it's like the more the worse the fuel gets. And so hydrogen is going to be pretty much the optimal fuel, and that's why the RD or the RS-25, which is the space shuttle engine, uses hydrogen, because the Americans, that was sort of like the pinnacle of American engine development, right? They put all their advancements together into the space shuttle, and so that uses hydrogen. Okay, so hydrogen is the most efficient fuel, but there's some drawbacks to hydrogen. So let's look at some other variables. Hydrogen is the most efficient, right? So we've got efficiency measured in seconds, which I just realized you guys don't understand why it's in seconds, but just this is a proxy for efficiency. But unfortunately, the hydrogen is very has a very like low density by volume. And so we need massive tanks to contain it. And these massive tanks are going to be taking up our payload mass. And remember, I mentioned that we already have like 95% of the entire rocket as fuel. So every bit of payload mass, or every bit of dry mass, as it's called, is precious. And so we don't want big tanks. Another problem with hydrogen is that it's a tiny molecule, and so it can pretty much escape through any pressure vessel designed to contain it. Eventually it will escape. And so it's sort of cumbersome to deal with long term. You got to burn it off very quickly. So let's jump over to this side, kerosene, right? And kerosene is actually off this chart. It has 10 to 16 carbons in a carbon chain. So it's even more inefficient than this one would be. But the benefits of kerosene are that it's liquid at room temperature, right? So it's super easy to deal with. We have a lot of experience dealing with it. But again, the efficiency just isn't there, right? And it also has those carbon chains which clog up our feed engine and engine plumbing. So methane, which is what the Raptors is using, it's sort of a Goldilocks fuel, right? So if we look back here at methane, we've got the most hydrogen we could possibly get without having the problems of hydrogen, right? We've got much higher density by volume, as you can see here, and or here. And additionally, the exhaust products are not that bad, and it's sort of an in-between fuel, right? Also, it can be made on the surface of Mars, which is crucial if you're trying to get back to Earth from Mars once you arrive there. There's no dead dinosaurs under the Martian surface that we can dig down and unearth and then burn in order to get out of the gravity well. So hydrogen, it adds too much weight and complexity and annoyance, and kerosene, it's just not going to work on Mars, and it's just inefficient in general. Methane is an in-between fuel that works great, and it's very practical. Combines efficiency with practicality. Okay, so so we talked about the fuel chemistry side of the optimization. Let's now talk about what the Russians were super focused on, which was engine plumbing, and just raising that combustion pressure and temperature as high as it can possibly go. So let's think for a second about how we might do this naively. Well, if we want to raise chamber pressure, we could just raise the tank pressure, because the tanks are feeding into the chamber, right? But again, if we want to raise it higher, we're going to get those tanks being overly massive, right? They're going to have to be super heavy to contain that much pressure, and that's not going to be good. So instead, we keep our tanks normally sized, and we use pumps to pump the gas into the combustion chamber at high pressure. These pumps could be powered by an external fuel source, and actually some rockets did use a third fuel to power their pumps. But people eventually realized, look, we've got a fuel line and an oxidizer line running right by this pump, this generator, why don't we just use that as the fuel to run the pumps? And so the gas generator cycle is this idea where you take some of your fuel from your fuel side, some oxidizer from your oxidizer side, you burn it in a pre-burner combustion chamber, which then will drive a turbine, which drives these pumps. And the exhaust from the turbine just gets chucked off the side. And you can actually see that this is the Merlin engine, which uses a gas generator cycle, and it's just chucking its exhaust from the pre-burner combustion chamber off the edge. And this is great. It's simple. It's efficient. You can get good pressure. But if you were paying attention to the enthalpy to kinetic energy emphasis of this talk, you'll notice that we're losing heat here. This exhaust gas is heat that could be converted partially into kinetic energy, and so it's not. It represents lost efficiency. So you might say, okay, well, let's just plug this back into the combustion chamber and have it feed in. And that is what a lot of rocket designers thought too. But that introduces some problems, right? So a few problems. So the first problem is that if you're using kerosene, which the Merlin does, then this partially burned exhaust is going to gunk up your plumbing. And I forgot to mention that this is run fuel rich because you don't want it to be at full temperature, because that would really stress the gas turbines. So it's fuel rich mixture getting pumped over this gas turbine. And if you pump the exhaust back in, you're going to gunk up your injectors. And you might say, okay, well, let's then just, instead of running it fuel rich, let's run it oxidizer rich to lower the temperature. Well, then you run into another problem, which is that your oxygen is much more reactive than your fuel. And so running superheated reactive gas over metal can be dangerous. So it might not be the best idea. The third problem is that once you connect the output of this turbine back into the combustion chamber, your shafts, your fluid is going to have to be flowing along these shafts at least for a tiny little bit, right? And so that represents a risk, because your exhaust, which is going to be fuel rich, could trickle over, or oxidizer rich, could trickle over to the oxidizer pump and then blow everything up. Or it could trickle over, or if it was oxidizer rich, it could trickle over to the fuel pump and then cause a failure there. So there's sort of these three problems emerge when you try and close the cycle, right? So that's what connecting the exhaust to the combustion chamber is, closing the cycle. And the Raptor engine using methane fuel solves all these problems. So let's look at how it does that. It uses something called a full flow stage combustion cycle. And so right off the bat, we get rid of this, fuel walking along the drive shafts problem by just splitting up our turbines. Now we have two turbines, we have two pre-burner combustion chambers. And so say a little bit of the exhaust gas walks along this shaft, it's only going to mix with more fuel-rich exhaust, right? So this is the fuel-rich turbine, this is the fuel-rich pre-burner, and this is the oxygen-rich pre-burner. And so there's no more issue with the mixing along these shafts, because it would just be oxygen mixing with oxygen, or fuel mixing with more fuel. Additionally, the fact that we're using methane now is a huge bonus, right? Because methane, again, is not as it's not as gunky and sooty as kerosene would be, and so we can really run it back into this combustion chamber without clogging much stuff up, which is great for reusability. On the oxidizer side, we still have that problem of the superheated oxygen being, having a reaction risk with the metal. But SpaceX developed a incredible alloy that is going to be very resistant to this reaction, and that seems to be working so far. So they haven't burned their turbines up yet with the superheated oxygen. So they seem to have solved that problem. So one more added benefit of this cycle is that, notice before we were running, a fraction of our gas through this pre-burner. Well, now we're actually running the entire flow, the entire fuel side, the entire oxidizer side through these pre-burners, and that's going to be really great because it's going to heat up our gases. Well, they're cryogenic initially. It's going to heat up our cryogenic liquids into superheated gases before they get to the combustion chamber, and that's going to make ignition really easy and really reliable. And that's really important, right? When you have a rocket engine that you're going to want to turn on and off like at least 50 times in its life cycle, reliability for reignition is important. And so that the fact that you're igniting gases and not cryogenic liquid is helpful. And so that is how the Raptor is going to be optimizing for chamber pressure and chamber temperature. And that's the end of my talk. So here are a couple of image credits. And here's just, I'll leave you with this picture of the Raptor, which is, I think is super cool. And I think this actually right here is the fuel rich turbine and pump stack right here. So that's just, it's cool to see it in real life. But thank you for coming and thank you for listening. If you have any questions, I'd love to answer them.
If you want to unmute and clap, you're welcome to do that.
Oh, I forgot I'm in sales.
Good job, Ted.
Yeah, Fred. Yeah, Fred.
Well done.
So any questions are welcome to go into the chat and I will call on you. All right, it looks like Hunter has one.
Hunter, you can unmute and say it.
So after graduation, are you going to go work at Blue Origin or SpaceX?
We'll see. I might need to work on some grad school acceptances before that, but
Well, I'll ask one while people think about it. So intuitively, I understand, if you raise the pressure and the temperature, that you would increase your velocity. But if I look at the equation, P1 was in the denominator. And so could you sort of go into a little bit more sort of
we can go back to that.
parsing that out? Yeah, I think it's on 21.
Right. So P1's in the denominator, right? But we've got one that's this ratio. And so we want to drive this term to 0 actually, in order to get this big parentheses term to be optimal. And I mean, you could also just take temperature 1 and then like use the perfect gas law to substitute in for pressure.
Yeah, that's how I figured it out, but I was caught in the last little bit. Kieran,
yeah.
do you want to ask yours?
Sure. So I could be mistaken, but it seemed like the analysis of your engine was done sort of assuming inviscid flow. How would that result you, that equation you derive, change if you accommodated for a viscous effects?
Yes, that's very good, Kieran. It would be, we are tacitly assuming inviscid flow. And I will show you where we get the change. The change is in this energy equation, where we have to add on. There's not a good closed form for it because it's a very non-conservative effect. For people that don't know, what Kieran is talking about is like viscous forces along the boundaries of the flow, and that causes inaccuracies in this model. But for now, we're just assuming that the edges are sort of perfectly smooth and the flow just goes right by without any friction or any heat transfer. And that actually it provides a useful insight for rocket design, because you want to get those walls of your combustion chamber and converging diverging junction as smooth as you possibly can. Any little bump is going to become a point where your kinetic energy gets converted back to heat, and it's just going to immediately melt through the wall of the rocket. So good thing to bring up, Karen.
Are there other questions? All right, well, if not, let's thank our speaker again. And I'm going to ask everyone else to head out. So
Thank you, Fred.
Thank you.
Thanks, Fred.
Thanks for coming, everyone.